applications given a rate of change function. So this is if we're given specifically, right, we can find antiderivatives of any continuous function, whether it's a rate of change or not. So now we're going to look at it specifically. We know it's a derivative. They've given me a derivative, a rate of change. All right, change in y divided by change in x. All right, so given a rate of change function, a derivative, we can find the exact change in a quantity using the fundamental theorem of calculus and the definite integral. The area above the x-axis is the positive change, the increase. The area below the x-axis is the negative change, the decrease. So if I'm talking profit, if I've got area above, that area is all the profit I gained. If I have area below, that would be all the profit I lost, right? I went into the negative. All right, and then the difference between the two, if it comes out positive, I had more positive profit than negative. If it comes out negative, I had more negative profit. It can also come out 0, which means the area above and below are the same. And so that would be the break-even point, right? Because I would have the same profit in the positive and the same profit in the negative. All right, given the rate of change, we can find it using the fundamental theorem of calculus. It's actually called the net change theorem. So this is specifically if we're given a derivative. All right, so I'm given a derivative that's continuous over an interval a to b. All right, so again, this is a derivative. Then I find a general antiderivative. The general antiderivative represents my original function. Now, it represents my original function without knowing what the constant is, but I don't need to know the constant because the constant's going to subtract out. And they talk about this in the MyLab videos, which, again, look at those, where they actually talk about this in pretty good detail. But then what it finds when I take my b and my a and I plug it in, it takes the function value of b, subtract the function value a, and so that's the net change, the exact net change in my original function, f of x, from point A to point B. All right, so if A is 2 months and B is 6 months, it tells me the difference in profit from the second month to the 6th month, if I'm talking in terms of profit. All right, so graphically, and again, we're going to actually do applications where we're given the graph. So again, we're given the derivative. All right, so the graph of the derivative, the rate of change function. So suppose this is my graph. Again, this is my rate of change. So it would be profit dollars per item, cost dollars per item, people per year, right? It's a rate of change function. And suppose we're looking from time A to time B, right? Then I'm going to mark off these points because they're important. This will be x1, this is going to be x2. All right, so if I'm thinking about this in terms of area, this would be an area, this would be an area, and this would be an area, right? Now, the area that I've highlighted in yellow would be a gain, right? Suppose this is area 1, this is area 2, this is area 3. And so from A to this first moment, this is an increase. And so area 1 would equal a gain. I'm adding that area. Area 2 would be a decrease, right? My slopes are negative, it's a decrease. And so area 2 would represent a loss. I'm losing all of that blue area, whatever it represents. If it's profit, I'm losing profit. If it's population, my population is declining by that much. All right, and then I switch again to area 3 is again a positive area, so this is an increase. All right, so I'm gaining that much area, right? I'm increasing that area. Now, just a quick make a note of how this goes back to what we talked about in chapter 3. This would be an end point. This would be an end point. This would be a critical, and this would be a critical. This is a critical, and this is a critical, right? Because it's where my derivative equals 0. If I've got a gain before my critical, so right, an increase, and then it switched to decrease, well, that means this critical is a relative max, right? Because I gained, stopped, and then lost, right? Go up, then down, so it would be a max. The second critical over here would be a relative min, right? Because I had a loss right before it. I decreased, stopped decreasing, and then I started to increase again. All right, so that would be a minimum, just to kind of reflect, and that's kind of important to remember when we get to applications. All right, then the integration. All right, so if I'm integrating this, so I'm taking my integral from a to b, right, my starting point a and my stopping point b of my derivative that's drawn here, which would be f of b minus f of a. Well, that would be area 1 plus area 3, right, the positive areas, the yellow areas, minus area 2, right, whatever that difference is. And based on this picture, it actually looks like I probably have more positive area. But it could come out positive, it could come out negative, and it could come out 0. Positive means I have more gains than losses. More negative area means I have more losses than gains. Right? If it comes out 0, it means the gains and losses are the same. The increase and decrease is the same. And so whatever that is, it comes out to that number. All right? That's the net change in whatever my function is. And so we're going to look at applications where all you're going to be given is the derivative function, its graph. And then you're going to know the areas, which we can find by integration. All right? And we're going to solve those. And so again, it's important to understand what this all means. If I'm given a derivative, when it's positive, I'm adding. When it's negative, I'm subtracting. Remember, increase when I'm above, decrease when I'm below. And then these are my critical values, which means those are my possible max and mins. My relative max and mins. And then my endpoints will also be where I could have absolute max and mins. All right, so we're going to look at I'm going to look at 2 applications where we're given the graph, and then we'll get to applications where we use the graph. I'm going to stop there and pick it up in the next video.